This is the second presentation in the two-dimensional motion packet for Mr. Sweeney's AP Physics C class. And today we're going to be talking about projectile motion. A projectile is any object that is acted upon only by gravity. And in this class we're going to speak about a bunch of different types of projectiles where gravity is the only thing acting on it. What that means is that there's no engines, there's no propellers, there's no thrust that's coming from any other source that is keeping these projectiles going. It's just gravity. And gravity, we've discussed this before, has a magnitude of a negative 9.8 meters per second squared, and that negative refers to the direction of gravity pointing downwards, as is our convention. All projectiles move in parabolic arcs, and it doesn't matter really where the projectile is starting. It can start horizontally or it can start at an angle. Here I've talked about angle projectiles moving in arcs, but horizontal projectiles would move in the same fashion. They would just start at the peak, so it would be half the arc. Now, if we're looking at the path of a projectile, we refer to the path of a projectile as the object's trajectory. So we would trace this object in an XY axis, and if we trace the path of it in an XY axis, X being the horizontal, Y being the vertical direction, that would be the trajectory of the object. And you can see this in the diagram in your notes and on the screen, where the object starts with an initial velocity, that would be v sub 0, and the dotted red line is the trajectory of this projectile, and you can see it is a parabolic arc. And notice between the initial velocity and the horizontal dimension given by the dashed blue line x, we have a angle there given by theta. And this is a common starting position for this initial velocity, theta. And we're trying to figure out what's happening with projectiles at different scenarios. If we want to know what affects the trajectory or the path of a projectile, there are two factors that affect this. The first being the angle that it's launched at. Shallower angles will not go as far if they're below 45 degrees. Greater angles will lead to greater heights. The other aspect or factor that's affecting this is the initial velocity of the projectile itself, where the greater the initial velocity, the greater range and height projectiles typically achieve. And here you can see a diagram or a picture showing someone throwing a ball, and they've identified the two main components here. First being the initial velocity and the angle it's launched at relative to the horizontal. When we talk about projectiles, the most central idea that allows us to analyze this motion is this concept of independence of motion. And what I mean by independence of motion is that the horizontal and vertical motions act independently of each other. So how the object is moving horizontally or side to side does not impact how the object or projectile would be moving vertically. This affords us a lot of advantages because from the vertical direct dimension, we can analyze things such as time and height. And from the horizontal direction, we can analyze range, or how far the object is going. Now the vertical direction acts only under acceleration due to gravity. So there's nothing else impacting the vertical direction. And contrast that with the horizontal direction. This has no acceleration. Acceleration due to gravity just acts vertically. So our horizontal motion will be constant, a constant velocity type motion. So vertically we're moving under the acceleration due to gravity. This is like a free fall problem. Horizontally we're moving with a constant velocity. And we take these two directions, vertical and horizontally, and analyze them independently. There is one variable that transcends both of them, and that is time. So the time that it takes vertically an object to rise and fall is the same amount of time that horizontally the object will be displacing. So let's look at these two directions independently. The vertical motion has an acceleration due to gravity which is always constant and is always a negative g, or a negative 9.8 meters per second squared. So this does not change. At the peak it's 9.8 meters per second squared, pointing in the downward direction. On the way up it's 9.8 meters per second squared, pointing downwards. On the way down it's 9.8 meters per second, pointing downwards. The initial velocity is found by determining the vertical component of the initial velocity. So not all projectiles are started purely vertically. Actually, that would be more of a free fall type problem. So there will be some sort of initial condition. Anything launched horizontally will have an initial condition in the vertical direction of 0 meters per second. And if it's launched at some sort of angle, we would use trigonometry to find out the vector component that is vertical, and we would use that as the initial velocity vertically. And we would take that vertical velocity and use that in a vertical motion analysis. Now, to denote our vertical versus our horizontal directions, we use the subscript y in order to identify our initial velocity, our acceleration, all these different aspects that occur only in the vertical direction. And the only thing that would be outside of this would be time. Again, time works for the horizontal and vertical. It does not have a designation or subscript. When we're looking at the vertical motion of an object that's undergoing projectile motion, that vertical motion is the same analysis that we did in a free fall type problem. So we've all seen a free fall type problem that is very similar to one half of a projectile. The only thing more sophisticated about a projectile is that while you are analyzing it vertically, there's also a horizontal component that's happening. We don't do the analysis at the same time. We solely just look at the vertical component and the horizontal component independently of each other. So because it's in free fall, and because it's undergoing acceleration due to gravity, the vertical component of velocity will change with time throughout the whole of its flight. And we can use our kinematics equations to figure out and do analysis on the vertical motion, but we must be sure to use only kinematic equations that have an acceleration component of it. And these are the three. These are in your AP Physics C reference table. You'll notice that in your AP Physics C reference tables, they're given as x's as opposed to y's. It really doesn't matter the dimension that we're working in. I've written them as y's because we are working in the vertical direction. And if you pulled this information off of your reference tables, you could treat the y direction the same as you could treat the x direction as far as applying kinematic equations for constant acceleration. Out of these three equations, the first one, y equals y sub 0 plus velocity initial in the y direction times time plus 1/2 acceleration in the y direction, t squared, is the most commonly used. That is probably the heaviest lifter as far as these three kinematic equations for the vertical direction. If we switch over to take a look at the horizontal motion here, in this dimension, acceleration is always 0. Acceleration due to gravity only impacts the vertical direction. In the horizontal direction, there's 0 impact on it. And the initial velocity is always found by finding the horizontal component of the initial velocity. So we have an initial velocity that's at an angle. It could have both a vertical and horizontal component contributing to it. And we would use our trig rules to find any horizontal component that we would be starting with. This initial velocity horizontally will remain constant throughout the flight of the object. And because of this, we use this equation. Velocity in the horizontal direction equals the change in position divided by time. Now you're not going to see this equation in your reference tables. It just relies on this idea that you understand that velocity equals the rate at which position changes. So coming this far, we can start looking at two scenarios where we have typical type problems for projectiles. The first one we're going to look at is a horizontal projectile. What this means to be a horizontal projectile is that an object is projected horizontally initially from some height. So it's thrown off a cliff horizontally, it's kicked off a building horizontally, a cannon launches something horizontally off a certain height. And the interesting thing about this type of scenario is that initially we'll have zero velocity in the vertical direction. So it's, in a vertical sense, very similar to a problem where we would drop some object from some height. So it's a free fall problem that would be dropped as initial velocity of 0, and it then accelerates downwards while horizontally maintaining its initial velocity. So there's no horizontal acceleration. In the vertical direction, we have a free fall problem, acceleration due to gravity. Our acceleration is always equal to a negative 9.81 meters per second squared. It's directed downwards towards the Earth. The initial velocity in the vertical direction, denoted by the subscript y, is 0 meters per second. And whatever velocity we start with will remain constant throughout our problem. Now I'd like us to look at an example of a horizontal projectile problem. In this example, Boba Fett rids himself of two rival bounty hunters, let's call them Kamsin and Jareg, by dropping them off a 15-meter high cliff. He drops one directly off the edge, but the other one has upset him, so he decides to fire him horizontally from a cannon instead. The two rival bounty hunters, they hit the ground, but they're 42 meters apart. What I want to know is with what velocity did the bounty hunter leave the cannon? At the heart of this problem is this idea that the horizontal velocity does not impact, or the horizontal motion does not impact the vertical motion here. So as both of them are dropped off the cliff, one is dropped directly down, one is launched horizontally, but they both start with initial velocity in the vertical direction of 0. So because that vertical direction does not impact or does not depend on what's happening side to side, it doesn't matter whether the bounty hunter is launched horizontally or not, it'll still take the same amount of time to hit the ground. So because they take the same amount of time to hit the ground, and is not impacted by, and their horizontal motion does not impact the time of their vertical fall, what we find is that we could determine the time it takes both bounty hunters to hit the ground. And this is the first step that we want to take. Once we have this time of the fall, we can go back and find out how far horizontally the launched bounty hunter moved, and divide that by the time to find what the velocity that he left the cannon with. So let's first find this time that it takes them to fall. And we use the equation position vertically equals the position initially vertically times the initial velocity vertically times time plus 1/2 acceleration vertical times time squared. So you'll notice I was very clear to say everything here is acting vertically because time always depends on vertical motion. Plugging into this, we can set the ground to be 0 meters and the height of the cliff to be 15 meters. Because velocity initial in the vertical direction is gone, this middle term here will go to 0, and we can just add to it this last term, which is 1/2 acceleration in the vertical, that's a negative 9.8 meters per second squared, times time squared. And using this equation, we can solve then for time, and we find that the time it takes them to hit the ground is 1.75 seconds. And this is the same time whether you're launched out of the cannon or whether you are dropped from the cliff. The fact that the launched individual is moving horizontally during the fall doesn't impact how long it takes that person to hit the ground. Now the horizontal distance between the two landing positions of the bounty hunters is equal to the displacement the fired bounty hunter undergoes during its flight. This depends on its launch velocity. Now we know how long it took them to hit the ground. We know how far apart they were when they landed on the ground. So we just need to figure out the rate at which that position was changed during the flight. That's the velocity. Velocity is equal to the rate of change in position divided by time. And that is 42 meters from the cliff, minus 0, that's the first bounty hunter. And that's divided by 1.75 seconds. It's how long it took either bounty hunter to hit the ground. In solving that, 42 divided by 1.75 equals 24 meters per second. For angled projectiles, this is the other common type of problem. In this scenario, instead of having an initial velocity vertically of 0, so you're dropping something, for an angled projectile you're going to have a vertical velocity that is non-zero. Typically this is angled upwards, though it can be angled downwards. You can go from a height and launch something at an angle that is vertically in the negative range. So when a projectile is thrown or launched at an angle above the horizontal direction, its initial velocity has both an x and y component. Its motion then will follow a parabolic path. There's a few things that are always constant when we talk about an angled projectile. The first is acceleration in the vertical direction. It is always 9.81 meters per second squared directed downwards. And ultimately these things are going to come to a peak. So whenever it does hit that peak, the velocity at this point will be 0 meters per second. This is an extremely important aspect of the problem because symmetry in the vertical direction requires that the path up and the path down, if they leave and land at the same position, will always be equal. So we can work around the peak, choose either the upward direction or the downward direction vertically, and understand all the concepts from either side. The most common application of this is finding the time to the peak and doubling it to find the time for the whole path. And again, regardless of what's happening vertically, the acceleration due to gravity that's happening there, horizontally there is no acceleration. The velocity in the horizontal direction will always be constant. So let's try another problem. This is a different type of problem, but an APC type problem that you'll see on an exam. It says that a projectile is launched from level ground with an initial velocity v sub 0. It has an initial velocity v sub 0. It has an angle theta with the horizontal. Now if air resistance is negligible, how long will the projectile remain in the air in terms of v sub 0 or initial velocity, acceleration due to gravity, and the angle above the horizontal is launched at theta? Note that the initial velocity, v sub 0, is not vertical or horizontal. It's some combination of the two. So we won't really work with v sub 0 directly. We'll work with the components of it, the vertical and the horizontal. So let's take a look at that. If we're just looking at the vertical direction, which is where we want to pay attention to because they're asking for time, and time will always depend only on the vertical motion. The initial velocity vertically will be the initial velocity at an angle multiplied by the sine theta, which is the vertical component. And we'll say that velocity at the y, so the end velocity, not the initial, we'll say that's 0 meters per second because we're going to end our range at the peak. So we'll go from the ground to the peak. Initially, it's initial velocity sine theta. At our final position, it's going to be 0 meters per second at the peak. We have a couple other values we could write down here. Acceleration in the y direction is a negative g, or a negative 9.81 meters per second squared. If we're going to use g as a symbol and not a value, we want to identify that it's negative so that we all understand that it's pointing downwards. And we want to find the time to the peak. This is our first step. They want to know how long it's in the air. Because of symmetry, if we find the peak, we can figure out the time totally by doubling whatever time we find to the peak. So we're going to find time to the peak, and then we'll just double whatever we find. So for this projectile example, because it's solely dependent on the vertical motion, again, we'll find that twice to the peak. And we'll use this equation to start off with. Velocity final in the vertical direction equals velocity initial in the vertical direction times acceleration due to gravity multiplied by time to the peak. Again, we're just finding the time for half. Rearranging this equation, we could say the time to the peak is equal to the initial, or to the velocity at the peak, which is 0, minus the velocity initial that it leaves with, divided by a. Now in this position, we've rearranged an equation that's in our reference tables, and in our next step we're going to try to do some substitution to get this equation into the terms that they're looking for. Remember, they're looking for velocity initial, which we do not have here. It's velocity initial in the vertical and velocity final. They're looking for acceleration due to gravity g, and they're looking for theta. So we're not in the terms we're looking for right now for t. But once we do some substitution, velocity final being 0 vertically, velocity initial vertically being velocity initial times sine theta, and acceleration being negative g. Once we have our substitutions in, now we are in the terms that we're looking for. And at this juncture, we're just looking at doing some steps of simplification. So if we take this equation that we substituted into, we could simplify it by getting rid of the 0 meters per second. That's unnecessary. And you have a negative in the numerator and a negative in the denominator, and those can go away as well. So the time to the peak is velocity initial times sine theta divided by g. It's not our total time though, because our total time is twice the time to the peak. So we multiply that expression by 2, and we find that the total time in the air is 2 times the initial velocity sine theta divided by g. And this equation works for every angled projectile that leaves the ground and returns to the same position it left with. So it's a universal equation, just using some of the values that we have out of our reference tables. This wraps up our notes for today. We do have a test coming up on this Thursday, and I will see you in class.